Here we have problem 17-3. The paraboloid is formed by revolving the shaded area around the x-axis. Determine the radius of gyration, kx. The density of material is constant. So we want to solve the equation I equals rho. Since it's constant, we can leave it out. R squared dV. Now that R, we're going to do a dV, which is a cylinder revolving around the x-axis, because we want it to be equidistant from the x-axis. So if we draw a cylinder here, right, every point on this cylinder is equidistant from the x-axis. And so we can put it in this equation. And then R will be the distance from the x-axis. We'll pick the y direction. If we revolve this point around it, it works out. So we're going to use I equals rho integral of y squared dV. So what is our dV? Well, we need, first of all, the area of the end as we're looking at that cylinder. So the area of the end is 2 pi r. In this case, we're using y. And the thickness of the cylinder, that's the circumference, the thickness is dy. So that's the area. And then the height here, or the length, is 200 millimeters minus x. And that x. Now, it's tempting here to use 0.1 and 0.2 as x and y, these smaller numbers. But the problem is, right here, we see we have a y squared and we have a 50x. So we can't have length squared equals length. So therefore, the 50 has units on it. And so changing it's not as simple as just putting a 0.1 on 0.2. So let's leave it in millimeters, and we'll make adjustments over here. So dV then is equal to the area, 2 pi y times 200 minus x dy. Now we don't want an x in our equation. So taking this equation here, we'll write x equals y squared over 50. So dV then is equal to 2 pi y, 200 minus y squared over 50 dy. Let's put that in over here. And now I is equal to rho, and let's bring out the pi, integral of y squared, and we got a 2 in front, because over here we got 2 and pi. The pi we took out front, 2 we'll leave in for now. And then so now we have y 200 minus y squared over 50 dy. Let's distribute this. So I is equal to rho pi integral of y to the third, 2y to the third would be 400 y to the third. And now we have y to the third and a y squared, so that's a negative y to the fifth. And then we have 2 divided by 50. And 2 divided by 50 is 0.04 dy. Okay, and we're going to integrate this from 0 to 100. Okay, integrating this, we have y to the 4th, 400, then divided by 4 be 100, minus y to the 6th, 0.04 divided by 6, from 0 to 100. If we put 100 into both of those, we get rho pi times 3.33 times 10 to the 9th. Now, the problem isn't asking for I, it's asking for radius of gyration, k. And the radius of gyration, k, is equal to the square root of I over m. We have I. Now let's solve for m. So m is equal to rho integral of dv. Now dv we already have here, so we'll integrate that rho integral of 2 pi, let's move the pi out, so rho pi 2 times y times 200 would be 400y, and 2y times that would be, again, negative 0.04 y to the 3rd dy. This is the same integral as the one up here, it's just that we didn't have the y squared. So now we have the mass is rho pi 200 y squared minus 0.01 y to the 3rd. Integrate that from 0 to 100 also. And that gives us pi, rho pi times 1 times 10 to the 6th. So k is equal to I over square root of I over m, and I is rho pi 3.33 times 10 to the 9th over rho pi 1 times 10 to the 6th. Rho pi cancels, and the square root of all that equals 57.7.